Data representation. Learning objectives. In this chapter, the user would learn the following in detail: number system, hexadecimal numbers, ASCII code, 2's complement, addition, subtraction, overflow, floating point representation. Data representation. Introduction. Definition. All data in a conventional digital computer is represented in binary form as a collection of ones and zeros. We can represent decimal numbers in binary and we can represent binary numbers in decimal. There are many representations that can be used, and there is no single best representation because each has its own characteristics in terms of impressibility, implementation cost, ease of conversions, and other considerations. Number system. When we type some letters or words, the computer translates them in numbers, as computers can understand only numbers. A computer can understand positional number system where there are only a few symbols called digits, and these symbols represent different values depending on the position they occupy in the number. A value of each digit in a number can be determined by using the digit, the position of the digit in the number, the base of the number system, where base is defined as the total number of digits available in the number system. Decimal number system. The number system that we use in our day-to-day life is the decimal number system. Decimal number system has base 10 as it uses 10 digits from 0 to 9, that is, decimal or base 10 number system with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In decimal number system, the successive positions to the left of the decimal point represent units, tens, hundreds, thousands, and so on. Representing decimal weights. Decimal number system with its 10 digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 is a base 10 system. Each position represents a specific power of the base 10. For example, the decimal number 1234 consists of the digit 4 in the units position, 3 in the tens position, 2 in the hundreds position, and 1 in the thousands position, and its value can be written as 1 multiplied by 1000 plus 2 multiplied by 100 plus 3 multiplied by 10 plus 4 multiplied by 1. 1 multiplied by 10 to the power 3 plus 2 multiplied by 10 to the power 2 plus 3 multiplied by 10 to the power 1 plus 4 multiplied by 10 to the power 0. 1000 plus 200 plus 30 plus 4. 1234. Binary number system. Uses two digits 0 and 1, also called base 2 number system. Each position in a binary number represents a 0 power of the base 2. Example 2 to the power 0. Last position in a binary number represents a multiplied by power of the base 2. Example 2 to the power x, where x represents the last position 1. Example, binary number 10101 to the base 2. Calculating decimal equivalent. Step 1. 10101 to the base 2. 1 multiplied by 2 to the power 4 plus 0 multiplied by 2 to the power 3 plus 1 multiplied by 2 to the power 2 plus 0 multiplied by 2 to the power 1 plus 1 multiplied by 2 to the power 0 to the base 10. Step 2. 10101 to the base 2. 16 plus 0 plus 4 plus 0 plus 1 to the base 10. Step 3. 10101 to the base 2, 21 to the base 10. Note, 10101 to the base 2 is normally written as 10101. Representing binary weights. Binary number system with its two digits 0, 1 is a base 2 system. Table shows the weighting for the binary number system up to 2 decimal places before and 3 places after the binary point. The least significant bit, LSB, is the rightmost binary digit, which has the lowest binary weight of a given number. The most significant bit, MSB, is the leftmost binary digit, which has the highest binary weight of a given number. Counting in binary is similar to the decimal number system. The LSB begins with 0 and is incremented until the maximum digit value is reached. The adjacent bit positions are then filled appropriately as the iterative counting process continues. Bit representation of binary numbers. A binary number system or the base 2 system uses only two symbols, namely 0 and 1. A binary digit is often called a bit. All the bits will have powers of 2, like 2 to the power 0, 2 to the power 1, etc. A 4-bit binary word is called as a nibble. An 8-bit binary word is called as a byte. A 16-bit binary word is simply called as a word, and a 32-bit binary word is called as a double word. Octal number system uses 8 digits 0, 1, 2, 3, 4, 5, 6, 7. Also called base 8 number system. Each position in an octal number represents a 0 power of the base 8. Example, 8 to the power 0. Last position in an octal number represents an x power of the base 8. Example, 8 to the power x, where x represents the last position 1. Example, octal number 12570 to the base 8. Calculating decimal equivalent. Step 1. 12570 to the base 8. 1 multiplied by 8 to the power 4 plus 2 multiplied by 8 to the power 3 plus 5 multiplied by 8 to the power 2 plus 7 multiplied by 8 to the power 1 plus 0 multiplied by 8 to the power 0 to the base 10. Step 2. 12570 to the base 8. 4096 plus 1024 plus 320 plus 56 plus 0 to the base 10. Step 3. 12570 to the base 8. 5496 to the base 10. Note: 12570 to the base 8 is normally written as 12570. Representing octal weights. The octal number system with its 8 digits 0, 1, 2, 3, 4, 5, 6 and 7 is a base 8 system. Table shows the weighting for the octal number system up to 3 decimal places before and 2 decimal places after the octal point. Just like the other counting conventions discussed previously, the LSB begins with 0 and is incremented until the maximum digit value is reached. The adjacent bit positions are then filled appropriately as the iterative counting process continues. Thus, the counting convention for octal is 0, 1, 2, 3, 4, 5, 7, 10, 11, 12, 13, 14, 15, 16, 17, 20. Bit representation. A single bit can be represented in 2 states, 0, 1. Therefore, if you take 2 bits, you can use them to represent 4 unique states, 0, 0, 0, 1, 1, 0 and 1, 1. And if you have 3 bits, then you can use them to represent 8 unique states, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 110 and 111. And if you have 3 bits, then you can use them to represent 8 unique states. These have a perfect correspondence to octal. 000 equals octal 0. 001 equals octal 1. 010 equals octal 2. 011 equals octal 3. 100 equals octal 4. 101 equals octal 5. 110 equals octal 6. 111 equals octal 7. With every bit you add, you double the number of states you can represent. Therefore, the expression for the number of states with n bits is 2n. Most computers operate on information in groups of 8 bits. Hexadecimal number system uses 10 digits and 6 letters 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Letters represent numbers starting from 10. A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F equals 15. Also called base 16 number system. Each position in a hexadecimal number represents a 0 power of the base 16. Example, 16 to the power 0. Last position in a hexadecimal number represents an x power of the base 16. Example, 16 to the power x, where x represents the last position 1. Example, hexadecimal number 19FDE to the base 16. Calculating decimal equivalent. Step 1. 1 multiplied by 16 to the power 4 plus 9 multiplied by 16 to the power 3 plus F multiplied by 16 to the power 2 plus D multiplied by 16 to the power 1 plus E multiplied by 16 to the power 0, all to the base 10. Step 2. 1 multiplied by 16 to the power 4 plus 9 multiplied by 16 to the power 3 plus 15 multiplied by 16 to the power 2 plus 13 multiplied by 16 to the power 1 plus 14 multiplied by 16 to the power 0, all to the base 10. Step 3. 65,536 plus 36,864 plus 3,840 plus 208 plus 14, all to the base 10. Step 4. 1,06,462 to the base 10. Note: 19FDE to the base 16 is normally written as 19FDE. Representing hexadecimal weights. Hexadecimal or base 16 number system provides 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9, 10, 11, 12, 13, 14, 15. Weighing for the hexadecimal number system up to 3 decimal places before and 2 places after the hexadecimal point. Bit representation. Hexadecimal numbers is a more complex system than using just binary or decimal and is mainly used when dealing with computers and memory address locations. By dividing a binary number up into groups of 4 bits, each group or set of 4 digits can now have a possible value of between 0000 and 1111, which is 8 plus 4 plus 2 plus 1 equals 15, giving a total of 16 different number combinations from 0 to 15. Don't forget that 0 is also a valid digit. The numbers 0 to 9 are still used as in the original decimal system, but the numbers from 10 to 15 are now represented by capital letters of the alphabet from A to F inclusive. And the relationship between decimal, binary and hexadecimal is given in the table. Code conversion. Converting from one code form to another code form is called code conversion. For example, converting from binary to decimal or converting from hexadecimal to decimal, etc. Decimal to code conversion. Decimal to binary. Divide the quotient by 2 and record the remainder. Repeat the above step until the quotient is equal to 0. The first remainder produced is the LSB in the binary number and the last remainder is the MSB. Accordingly, the binary number is then written from left to right with the MSB occurring first. Example: 37 equals 100101. Decimal to octal. Divide the quotient by 8 and record the remainder. Repeat the above step until the quotient is equal to 0. The first remainder produced is the LSB in the octal number and the last remainder is the MSB. Accordingly, the octal number is then written from left to right with the MSB occurring first. Example: 214 equals 326. Decimal to hexadecimal. Divide the quotient by 16 and record the remainder. Repeat the above step until the quotient is equal to 0. The first remainder produced is the LSB in the octal number and the last remainder is the MSB. Accordingly, the octal number is then written from left to right with the MSB occurring first. Example: 3509 equals DB5. Binary to code conversion. Binary to decimal. Binary is a base 2 system. Each digit represents an increasing power of 2, with the rightmost digit representing 2 to the power 0, the next representing 2 to the power 1, then 2 to the power 2, and so on. To determine the decimal representation of a binary number, simply take the sum of the products of the binary digits and the powers of 2 which they represent. For example, the binary number 100101 is converted to decimal form by 1 multiplied by 2 to the power 5 plus 0 multiplied by 2 to the power 4 plus 0 multiplied by 2 to the power 3 plus 1 multiplied by 2 to the power 2 plus 0 multiplied by 2 to the power 1 plus 1 multiplied by 2 to the power 0, which equals 1 multiplied by 32 plus 0 multiplied by 16 plus 0 multiplied by 8 plus 1 multiplied by 4 plus 0 multiplied by 2 plus 1 multiplied by 1, which equals 37. Binary to octal. Break the binary digits into groups of 3 bits starting from the binary point. Convert each group on its appropriate octal digit. For whole numbers, it may be necessary to add a 0 as the MSB in order to complete a grouping of 3 bits. Similarly, When representing fractions, it may be necessary to add a trailing zero in the LSB in order to form a complete grouping of 3. Example 110101 equals 65. 10111 equals 27, which is 010111. Binary to hexadecimal. To convert a binary number into its hexadecimal equivalent, divide it into groups of 4 bits. If the number of bits isn't a multiple of 4, simply insert extra 0 bits at the left, called padding. For example, 1010010 to the base 2 equals 0101 0010 grouped with padding equals 52 to the base 16. 11011101 to the base 2 equals 11011101 group, which equals DD to the base 16. Octal to code conversion. Octal to decimal. Get the decimal equivalent of octal. Multiply every digit with 8 power of digit location. 0 based 37246. 6 location is 0, 4 location is 1, 2 location is 2, 7 location is 3, and the 3 location is 4. Sum all the multipliers. Example 345 equals 229. Octal to binary. Converting from octal to binary is as easy as converting from binary to octal. Simply look up each octal digit to obtain the equivalent group of 3 binary digits. Octal equal to 3, 4, 5. Binary equals to 011, 100, 101, which equals 0111 001 01 binary. 345 equals 0111 00101. Octal to hexadecimal. When converting from octal to hexadecimal, it is often easier to first convert the octal number into binary and then from binary into hexadecimal. For example, to convert 345 octal into hex, octal is equal to 345. Binary is equal to 011 100 101, which equals to 0111 00101 binary. Drop any leading zeros or pad with leading zeros to get groups of 4 binary digits, bits. Binary 0111 00101 equals 1110 0101. Then look up the groups in a table to convert to hexadecimal digits. Binary equals 1110 0101. Hexadecimal equals E5, which equals E5 hex. Therefore, through a 2-step conversion process, octal 345 equals binary 0111 00101, which equals hexadecimal E5. Hexadecimal to code conversion. Hexadecimal to decimal. Get the decimal equivalent of hex from table. Multiply every digit with 16 power of digit location. 0 based 7DE. E location is 0, D location is 1, and the 7 location is 2. Sum all the multipliers. Example, 7DE is a hex number. 7DE equals 7 multiplied by 162 plus 13 multiplied by 161 plus 14 multiplied by 160. 7DE equals 7 multiplied by 256 plus 13 multiplied by 16 plus 14 multiplied by 1. 7DE equals 1792 plus 208 plus 14. 7DE equals 2014 in decimal number. Hexadecimal to binary. Get the binary equivalent from the table. For example, 1e3 to the base 16 equals 0001 1110 0011 to the base 2. Hexadecimal to octal. For example, the equivalent octal number for 25b to the base h can be derived as hex to binary conversion. 2 equals 0010, 5 equals 0101, b equals 1011. The binary number 0010, 0101, 1011. Now the hexadecimal equivalent binary numbers can be converted into equivalent octal numbers. To do so, split the binary number into segments having 3 bits each to find out the equivalent octal for the binary number. 001 equals 1, 001 equals 1, 011 equals 3, 011 equals 3. The octal number is equal to 1133 to the base 8. ASCII code representation. American Standard Code for Information Interchange Coded Character Set for Information Interchange. It has become a world standard alphanumeric code for microcomputers and computers. It is a 7-bit code representing 27 equals 128 different characters. These characters represent 26 uppercase letters A to Z, 26 lowercase letters A to Z, 10 numbers 0 to 9, 33 special characters and symbols, and 33 control characters. The 7-bit code is divided into 2 portions. The leftmost 3 bits portion is called zone bits, and the 4-bit portion on the right is called numeric bits. An 8-bit version of ASCII code is known as USACC II8 or ASCII 8. The 8-bit version can represent a maximum of 256 characters. For character data type, its representation uses codes such as the ASCII, IRA, or EBCDIC. ASCII table representing the data. Table shows the ASCII data. Complement representation, ones complement. In this type of representation, the magnitude portion is shown in the complement form. The ones complement of a number is obtained by complementing each bit. All ones are made zeros and all zeros are made ones. The following examples illustrate ones complement formation. Magnitude 0111, ones complement 1000, magnitude 1000, ones complement 0111, magnitude 1001, ones complement 0110. In ones complement representation, a positive number is represented without any change, similar to signed magnitude form. But the negative number representation differs. The sign bit is 1 and the magnitude portion is put as ones complement. Complement representation, 2's complement. The 2's complement of a number is attained by adding 1 to the ones complement of that number. The following examples illustrate 2's complement formation. In 2's complement number system, a positive number is represented in the original form similar to the signed magnitude form. In the case of negative number, the sign bit is 1 and the magnitude is put as 2's complement. The 2's complement representations are very useful for the arithmetic operations. 2's complement addition. An example of 2's complement addition using 8-bit notation. when adding two positive numbers, their sign bit's most significant bit will both be 0. So the numbers are written and added as a pure 8-bit binary addition. Decimal 10 plus 2 equals 12. 2's complement binary 00001010 plus 00000010, which equals 00001100. 2's complement subtraction. The simplest case of 2's complement subtraction, where one positive number, the subtrahend, is subtracted from a larger positive number, the minuend. In this case, the minuend is 17 to the base 10 and the subtrahend is 10 to the base 10. Because the minuend is a positive number, its sign bit MSB is 0, and so it can be written as a pure 8-bit binary number. The subtrahend is to be subtracted from the minuend and so needs to be complemented simple ones complement and 1 added to the least significant bit LSB to complete the 2's complement and turn plus 10 into minus 10. When these three lines of digits and any carry 1 bits are added, remembering that in 2's complement any carry from the most significant bit is discarded. The answer, the difference between 17 and 10, is 00000111 to the base 2 is equal to 7 to the base 10, which is correct. Therefore, the 2's complement method has provided correct subtraction by using only addition and complementing, both operations that can be simply accomplished by digital electronic circuits. Overflow. Signed binary numbers are of a fixed range. If the result of addition or subtraction goes beyond this range, overflow occurs. Two conditions under which overflow can occur are: positive add positive gives negative, negative add negative gives positive. 2's complement addition overflow rule. If two 2's complement numbers are added and they are both positive or both negative, then overflow occurs if and only the result has the opposite sign, that is, plus A plus B equals minus C, or minus A plus minus B equals plus C. Example: calculate minus 7 plus minus 6 using a 4-bit 2's complement representation. Minus 7 is 1001 plus minus 6 1010 plus 3 10011. Overflow. 2's complement subtraction overflow rule. If two 2's complement numbers are subtracted and their signs are different, then overflow occurs if and only if the result has the same sign as the subtrahend. Plus A minus minus B equals minus C, or minus A minus plus B equals plus C. Example: calculate 7 minus minus 6 using a 4-bit 2's complement representation. Floating point representation. Fixed point numbers have limited range. To represent very large or very small numbers, we use floating point numbers. Examples: 0.23 multiplied by 10 to the power 23, very large positive number. 0.5 multiplied by 10 to the power minus 32, very small positive number. Minus 0.1239 multiplied by 10 to the power minus 18, very small negative number. Floating point numbers has three parts: sign, mantissa, and exponent. The base, radix, is assumed, usually base 2. The sign is a single bit, 0 for positive number, 1 for negative. Mantissa is usually in normalized form. Normalized form. The fraction portion cannot begin with 0. More bits in exponent gives larger range. More bits for mantissa gives better precision. Exponent is usually expressed in complement or excess form. Example, express minus 6.5 to the base 10 in base 2 normalized form. Minus 6.5 to the base 10 equals minus 110.1 to the base 2, which equals minus 0.1101 multiplied by 23. Assuming that the floating point representation contains 1-bit sign, 5-bit normalized mantissa, and 4-bit exponent, the above example will be represented as 1, 11010, 0011. Example, express 0.1875 to the base 10 in base 2 normalized form. 0.1875 to the base 10 equals 0.0011 to the base 2, which equals 0.11 multiplied by 2 minus 2. Assuming that the floating point representation contains 1-bit sign, 5-bit normalized mantissa, and 4-bit exponent, the above example will be represented as 0, 11000, 1101 if exponent is in 1's complement, 0, 11000, 1110 if exponent is in 2's complement, 0, 11000, 0110 if exponent is in excess 8. Conclusion. In this chapter, we have covered the following aspects of data representation: number system, hexadecimal numbers, ASCII code, 2's complement, addition, subtraction, overflow, and floating point representation.